The goal here is to find the Nash equilibrium in two-player games using a path-following algorithm. This will show that this searching problem is in PPAD class, and we expect that such an algorithm will be the most efficient algorithm. This algorithm is the Lemke-Howson algorithm. The Lemke-Howson algorithm is based on labels. The set of labels is equal to the set of actions of the players. Therefore, there is one label per action of every player. Given a strategy profile, the labeling function returns a subset of the possible labels. A strategy profile is completely labeled solution if the labeling function returns the complete set of labels. That is, one label for every possible actions of all the players. Instead, a solution is almost completely labeled if the labeling function returns the complete set of labels except one. So, except the label of one action of a single player. This is the labeling function used by Lemke-Howson. Specifically, the label of an action is the subset of labels returned by the labeling function if and only if either the probability with which such an action is played is 0, or the value the player gets by playing such an action is equal to Vi, that is, the value of the best response of the player. So, summarily, either an action is not played or it is a best response. A strategy profile is a Nash equilibrium is if and only if it is completely labeled. Consider this example with 3 actions per player. Here we have the strategy spaces of the two players. The strategy space of player 1 is on the left, while the strategy space of player 2 is on the right. Initially, for the labeling, we consider only the conditions related to the fact that an action is played with 0 probability. Consider initially the simplex of player 1. All the solutions in which the strategy of player 1 is on the blue plane have label A1. Similarly, here all the solutions in the yellow plane have the label A2. Here label A3. Consider the simplex of player 2. Here all the strategy of player 2 that are on the green plane have label A4. Here A5 and here A6. Now, for the labeling, we consider the condition requiring that an action is a best response. Consider the simplex of player 2. We divide the simplex in terms of best response areas as usual. This means that, for instance, if the strategy of player 2 is into the red region, we have the label A3. Consider now the simplex of player 1. We divide the simplex in best response areas as before. It can be observed that in each simplex, all the labels appears, and given a simplex, each label appears only in a single area. The Lemke-Howson algorithm does not work in the whole strategy of the profile space, but only on a finite number of strategy profiles. Specifically, we are interested in all the strategy profiles in which the number of labels is maximal. In particular, we are interested in nodes, obtained by the intersections between the best response conditions and the simplex borders. Here an example. Focus on the simplex of player 1. If a strategy is on the vertex, it has 3 labels. If it is on a border, just 2 labels. Otherwise, only 1 label if it is in the inner of a best response area. So our interest is in working exactly on the nodes that are the vertices, that are the points in which the number of labels is maximal. So a solution is a pair of nodes, one on the simplex of player 1 and another on the simplex of player 2. Here you have an example. Any solution collects two ham labels, where ham is the number of actions of each player, and these labels are potentially non-different. That is, some label could occur multiple times. Here you have an example. The labels gotten in the simplex of player 1 are A3, A4, A5, while the labels in the simplex of player 2 are A2, A3, A5. Notice that labels A3 and A5 appear twice. In an almost completely labeled solution, a single label appears twice. This means that this label is gotten both in the simplex of player 1 and in the simplex of player 2, since we cannot take the same label twice in a single simplex. Here an example of almost completely labeled solution in which the label A2 appears twice. If we want to discard one of the two occurrences of the same label that appears twice, we have two ways to do that. Either losing such a label in the simplex of player 1, moving to another strategy, or in the simplex of player 2. Look at the simplex of player 1. Moving from a node circling in red along the green arrow, we lose the label A2. Look at the simplex of player 2. Also here, moving from the node circling in red along the green arrow, we lose the label A2. As a result, we have that almost completely labeled solutions induce path. This is because if we reach an almost completely labeled solution from an almost completely labeled solution, then there is only one way to move to the next almost completely labeled solution. The Lemke-Howson algorithm is rather simple. It starts from an artificially completely labeled solution that is not a Nash equilibrium. This artificial solution is given by a strategy playing zero probability for every action of every player. Obviously, this is not a well-defined strategy. Then, the Lemke-Howson algorithm moves to an adjacent solution, losing a label and making another label appearing twice. And finally, the Lemke-Howson algorithm follows a path of almost completely labeled solution until a completely labeled solution is not found. Here the example. We start from the artificial solution, which has all the 6 labels: A1, A2, A3, A4, A5, A6. We discard the label A1 and we move along the red arrow, getting label A4. This means that A4 appears twice, and we need to discard one of the two occurrences. The second occurrence is in the simplex of player 2. In order to lose the label A4 in the simplex of player 2, we need to move along the red arrow. Now we have that the label A3 appears twice, and we need to lose label A3 from the simplex of player 1. We do that moving along the red arrow. Now we have that label A6 appears twice. In order to lose A6 in the simplex of player 2, we move along the red arrow. So we have that label A2 appears twice. In order to lose A2 in the simplex of player 1, we move to the center of the simplex. Now we have that label A5 appears twice. We lose A5 in the simplex of player 2, and we find a completely labeled solution that is a Nash equilibrium. In general, starting from the artificial solution, we have many different options. Each option corresponds to an action of some player. In addition, each option corresponds to a different path. When there is only one Nash equilibrium, all the paths lead to the same equilibrium. Otherwise, each path can lead, in principle, to different Nash equilibria.